Hi everyone, and welcome to our math review. The learning goals for today are the following. So today I'm planning to cover vectors, the concept of vectors, how vectors behave. So we will cover a little bit of the product, the cross product, the meaning of those operations. Also, I will explain the difference between vectors and points. This is very, very important in computer graphics in particular. I will explain a couple of concepts that maybe are new for you. These are bivectors and trivectors. I will talk a little bit about matrices, and we will see everything around a coding example that will produce something really cool and very useful in computer graphics. I hope you like it. So let's start by saying that the notation that I will use on most of the lectures is this one for angles, scalars, vectors, matrices, planes, triangles, and everything. This is a notation that appears on page 5 from the book Real-Time Rendering by Thomas Akanin Moller. So if you want to, please go and check that page. This notation in particular is not in page 5, I think it's in page 7, but please read that section from the book, and we will try to use this notation. Sometimes we can use a different notation, but we will explain why. And if for some reason I am not using this, again, it's either because it is on purpose and I will tell you, or it is because maybe I made a mistake. So if you find a mistake eventually in one of the presentations, just tell me. But this is a notation. So let's first try to understand what is a vector, because vectors are probably the most important mathematical entity that we use in computer graphics. And in my opinion, they can be confusing sometimes. And there has been a confusion in general in mathematics among like different areas of mathematics, between linear algebra and geometric algebra and like different stuff. So the thing is, if we ask what is a vector, it depends who is asking. So that is what I want to explain right now. And I want to explain that the meaning of a vector depends on the perspective from which we are asking this question. So I think this will fix most of the confusion. So the thing is, we have a programming perspective or programming point of view, a mathematical point of view, and a geometric point of view, right? And depending on what are we talking about, we can have different interpretations, right? So let's get rid a little bit, right, for a moment of the word vector, okay? So, and let's jump into in my opinion, the most basic interpretation, at least for us as computer scientists, that is the programming perspective, okay? So from the programming perspective, a vector is just data, okay? So it usually is just an n tuple of real numbers. That's it. From the programming perspective, that's it. Only 2 or 3 or 4 real numbers. And yeah, and usually we can have like different type of, we can code different type of classes for vectors, and obviously we can do this cross product, dot product operations, wedge operations in case of geometric algebra and all that like that. But again, they're just a collection of numbers. So for now, let's not say the word vectors. Let's call data. Okay? So we are computer scientists. We code. This is just data. So this data, from the mathematical perspective, is just a matrix, right? As mathematicians, this is just a matrix. Usually, if you see different computer graphics books, depending on who wrote that book, you will see different notations. So sometimes you will see notation in a row fashion or in a column fashion. So in general, if the person that writes a book is a mathematician, they usually like to write vectors as columns. And yeah, and other people, I think most like computer science, not as mathematics side, so they used to use the row notation. And this is actually very important. It's not just like how do you write it, right? And sometimes some books are saying, oh, this is better, the row version is better because it's just shorter, or it's just easier to put in a book, right? Because it's like aligned with the paragraphs. Yeah, that's true, but the thing is, depending on which notation you're using is the way you process certain operations, specifically with matrices. But I will explain that later. But for now, let's just understand that from the mathematical perspective, this data, right, is just a matrix. And again, from the mathematical side, it is usually represented as a column. And also sometimes, if it's written as a row, they read it as the transpose, right? The transpose of that matrix. And usually the components of that matrix are usually labeled with the name of the axis to which they correspond. So now let's understand what is that. What are those axes, right? So those axes are related with the geometric perspective or the geometric interpretation, right? So those axes are usually orthogonal axes or linearly independent axes. And this is very important that I am saying usually, because they're not always orthogonal. You will see that when we talk about coordinate frames, we will see that a coordinate frame has basis vectors, and those vectors they're not necessarily need to be orthogonal. But for now, let's pretend that they're orthogonal. And so, for example, this is a basis vector called x and y. So for this data, right? This data, it's a tuple of two numbers, two real numbers. It has two components, right? So one component is ax, and the other component is xy. Perfect. The thing is that the geometric perspective could have different interpretations, right? Again, it depends of who is asking. So the geometric interpretation, if we are talking about linear algebra, right? It says that this data can represent a position or a vector. And in the case of linear algebra, a vector is a direction with a magnitude, right? Again, because we are talking about different perspectives. So for example, if we were talking about physics perspective, it will be a force with direction, right? A force with a magnitude and direction. But we are not physicists, so we are in this case just talking about a direction with a magnitude. So now we finally see the name vector, right? We were talking about the data. We were talking about a collection of real numbers that in the case of a geometric interpretation from the perspective of the linear algebra can represent a position in space or a vector that is representing a direction with a magnitude. There's another interpretation, the geometric algebra perspective, right? So in geometric algebra, this data can represent a position or a vector that is a directed length. In geometric algebra is a directed length. It sounds similar, right? Because in linear algebra, we say that a vector is a magnitude with a direction, or a direction with a magnitude. So saying directed length kind of makes sense, right? It's similar. So here's the interesting part. It can also represent that same data. It can also represent a bivector. And the bivector is a directed area. Wow, this is getting crazy. This is getting weird. And it also can represent a trivector, which is a directed volume. Okay? all those four things can be written in a coding, right, in programming, can be expressed with exactly the same thing. Okay, great. So now let's jump into trees to the max. Okay, so now we are in trees to the max, and I have two spheres here, A and B, and these spheres represent positions, right? They represent a position on an Euclidean space. They are actually in a 3D space, in a 3D Euclidean space. So we have x, y, and z axis. So this is x, this is y, and the vertical one is z. In different softwares, sometimes the vertical axis is z, sometimes the vertical axis is y. In this case, the vertical one is z. So if I go to the top view, I am seeing everything from a planar view, in this case only the plane xy. So in this case we're kind of seeing the world from a 2D perspective, right? And again, these objects here represent position. When I click, I can see the axis or the basis vectors of this Euclidean space, the basis vectors x and y, and I can move them. Okay, I can see their positions here, right? But also I could open this window here, and I could access in code, I could access the positions, the data that we were talking about, like this. So I will call the object by this symbol, then the name of the object, and then dot pos. Okay, shift enter, and this is the position of this object. So I will increase the size. Yeah, so this is the position of A. Now let's check the position of B, right? It's different, obviously. And this is the type of data that we were talking about, right? It's just a collection of three real numbers. Good. So now let's try to understand the difference between positions and vectors. So a position in space, okay, it has a corresponding vector. So for each position in space, we have a corresponding vector, right, that has magnitude and direction. We have A and B positions and A and B vectors. So for now, I will hide the spheres, I will hide the positions, and I will just keep the vectors, okay? So again, a position has a vector, a corresponding vector, and the vectors have, in some sense, they have two corresponding positions. One is the tip of the vector, that is the position that they are representing, and the other one is its origin, which right now it's 0, okay? So in practical terms, because we are using exactly the same data to represent the vectors and the positions, these vectors all begin, or they are all start in 0, 0, 0, okay? In exactly the origin of this Euclidean space. Okay, so when two vectors have the same direction, not necessarily the same length, right, but the same direction, we usually say that those vectors are collinear. You can also say that they are linearly dependent, and this means that there is a scalar number, a real number, that I can multiply. In this case, I could multiply B to get A, or I could multiply A to get B. That means that they are linearly dependent between each other. You can also say that they both lie on the same one-dimensional subspace of this Euclidean space. And it sounds weird. What is a one-dimensional subspace? Well, one-dimensional subspace in an Euclidean space is just a line that is passing through the center of that space. So if I, for example, grab this vector here and I modify, right now I can move it on x, y, and z, right? But I can move it on its local axis. In this case, is its exactly its direction, right? So you can see that exactly in this line, right, in this direction, there can be infinite number of vectors, right? And all the vectors that lie on the same in that same line, they'll all be collinear, they will be linearly dependent, and in the end, they are lying in the same one-dimensional subspace. This will be very relevant. Eventually, it will be very relevant when we talk about projective geometry, and that will lead us to create a projection camera, right? That is one of the almost the most important thing in computer graphics in 3D, right? Create a camera that can represent perspective views flattened in 2D. Okay, so now let's talk about like how vectors behave. There are a couple of things that you must know. Again, the intention of this math review is not to explain again what you already saw in linear algebra, but to give you a geometric insight or geometric interpretation of those things that you should know already, and a little bit of more modern stuff regarding geometric algebra. Okay, so for example, we already know that if you want to add vectors, right? It's kind of taking this vector and put it here, right? So it becomes a parallelogram, right? We already know that. You probably know that we have two important products in linear algebra, the dot product and the cross product. So let's talk about those. Okay, so first let's talk about the dot product. So the dot product is defined as the sum of the products of each component of each vector. And the result of the dot product is a real number. And you can see an example of this result here. So the most important concept of dot product is to understand that it measures the similarity of two vectors. If two vectors are exactly the same, so the angle between those vectors is exactly zero, they are exactly collinear or linearly dependent, the dot product will be 1. Okay? So they are exactly the same. As you start moving these vectors and they start to have a different angle between them, so 30, 45, 60, whatever, you start to get different value on the dot product. So the things that you usually need to remember is that if they are equal, exactly the same, you'll be 1. If they are orthogonal between them, the result will be 0, right? So 90 degrees from them, for this orthogonality, they will be 0. And if the two vectors are opposite vectors, right? They have 180 degrees, it will be -1, right? Of course, the same repeats on the other side. So the dot product in 3 dimension, it should look like this, right? So we denote dot product with the center dot, and again in 3 dimension it will be ax times bx plus ay times by plus az times bz. Okay, so in terms of coding, is very easy, and most of I mean, you already have those functions already in WebGL and 3.js. I mean, yeah, most packages. Specifically, the ray tracer that you will need to write, you will need to create your own functions, your own dot product, cross product functions. Okay, but yeah, but it's very easy. So now let's talk about the cross product. So the cross product is a little bit different because it measures the difference of two vectors. So the cross product of the vector product, so sometimes it's also called vector product, it will return a new vector that is perpendicular to both vectors. So as we said before, each vector has two positions or two corresponding positions. One is its tip, right? That is the actual position on space that this vector is representing, and the other is the origin, right? So if you take any two vectors with their two corresponding positions each, right? One of those is exactly the same because A and B have the same origin. So in the end, it's kind of, we could say that we have three points, right? So if you have 3 points in space, what you have is a triangle. And a triangle is a geometrical entity that is perfectly planar. It always defines a plane, right? So the resulting vector from a cross product is a vector that is orthogonal to that plane. This is usually how we can, for example, compute the normal of a surface. If you don't understand what a normal is, I will explain that later from the people that already know. The normal is basically the direction of a surface, right? The direction the direction of a surface. So we usually define it or compute it by taking, if that surface, for example, is a mesh surface, is a polygon surface, we take one of the triangles on the point of the surface we are interested, and we just take the cross product between two edges of that triangle, and we get a new vector that is perpendicular to that plane, and that is the normal direction. So this is how you code a cross product. So as you see, this is the result of the cross product because it's not a real number, it's a vector, right? Or it's a data, right? In the end, it's exactly the same. In the end, it's a vector, so it's a data that is a collection of 3 real numbers, right? So I just put different colors to each x, y, z value, right? So all this will become in the x component, y component, and z component of this d vector that is the cross product vector between A and B. Something that is also super important is that the cross product follows a right-hand rule. Right-hand rule means that if I take A cross B, and imagine that you have your hand the fingers of your hand are first pointing through A and then rotating through B, right? Your thumb will be pointing to D. If I do exactly the opposite, B cross A, the vector will be opposite. So it will be pointing down, okay? Right now, this is not very important, so let's just keep going. But it will be very important in the future. Okay, so let's see an animation and how it looks. So this is basically how a cross product looks, right? Between B and A, or A and B, right? You have a triangle, and the dot product result, sorry, the cross product result, that is this purple vector here, it will be always perpendicular to that plane, right? And you might observe already that this, the way this purple vector is changing is not only changing in its direction, but also in its magnitude, right? So maybe some of you are wondering, okay, perfect, okay, I understand. The direction, it will be always orthogonal to that plane, but what happens with the magnitude? So let's try it now, right now, to restrict the cross product to a pair of vectors that are on the xy plane, okay? So if the two vectors are restricted to the xy plane, as you can see, the direction of the resulting vector is not changing, but what is changing is its magnitude. So it turns out that its magnitude is related with the area of the parallelogram that is formed by these two vectors. And by the way, this is exactly the same parallelogram that happens when you sum or add these two vectors, right? So if you take vector A and you add to vector B, what you will obtain is this position right here, right? You form a parallelogram and you will obtain this position. Well, this entire area is the magnitude of this resulting vector. So the resulting vector from a cross product will have as magnitude the area of the parallelogram between these two vectors. And this is, again, very convenient for some computer graphics computations. For example, there's something called barycentric coordinates, that we will cover eventually. And for computing the barycentric coordinates, you usually need to compute the area of a triangle, right? So if you already know that the magnitude of the cross product is the area of the entire parallelogram, it means that the area of the triangle formed by these two vectors is just half of that area, right? So usually that is a very convenient way to compute the area of a triangle, is half of the magnitude of the cross product between two vectors from the triangle, okay? And you will use that for barycentric coordinates, that is applied to textures, and is also applied to ray tracing. So everything is connected and it's super interesting. But everything comes from here. Okay. Great. So this is a cross product, and we are talking about linear algebra right now. Now let's jump to geometric algebra. Well, it turns out that what we call cross product in linear algebra, it's called wedge product in geometric algebra. And in 3 dimensions, it's exactly the same. It's exactly the same formula, and it's exactly the same code. It just have a different name, okay, and different symbol. This is the symbol we use in geometric algebra to define the wedge product. And the geometrical interpretation of this in geometric algebra is different. Again, in linear algebra, we said that the result of the cross product is another vector with its own magnitude and direction. But through the eyes of geometric algebra, the result of a wedge product is a bivector that is a directed area. So we already know that the cross product is related with this area, right? Its magnitude is this area. Well, for geometric algebra, this is the result, right? The area is the result. It's a directed area. Again, the formulas are exactly the same. But yeah, you will see that depending on the position on those two vectors, A and B, the result is this bivector that is obviously changing over time. But again, the result in the end is exactly the same 3 real numbers. And this is very important because, at least for me, this concept of bivector was very confusing at first. I remember that I was thinking when I started to study this type of things, I heard bivector and I was seeing these diagrams of these two vectors and this directed area, and I thought that the data was a little bit more complicated, that I had more numbers, right? Well, it turns out that no, you don't have more numbers. So the result of the wedge product is exactly the three real numbers that can represent a position in space, or this purple vector in space, and that's it. You don't have more information. So for example, at least to the best of my knowledge, if you have the bivector, which is just a collection of three real numbers, you cannot decompose a bivector in its original 2 vectors that you took from which you took the wedge product to produce this bivector, right? It's not possible. You don't have more information. In the end, the data you have is just 3 real numbers, and that's it. So in terms of this bivector, is just a geometrical interpretation on geometric algebra, but it's very useful because geometric algebra, the goal of geometric algebra is seeing geometric entities as algebraic entities. So the idea here is to grab geometric entities and play with them as algebraic elements. So you could add those elements or multiply those elements, and the results of those operations should be also a geometrical object, right? That it should have some meaning. And it is very interesting and it is very useful. So in specifically bivectors, we will use bivectors for rotate objects, and it's related to rotors and quaternions. and you will see that in the future. But for now, let's just keep with this geometric interpretation. Okay, so as we said, the cross product or the wedge product, again, the formula is exactly the same in 3 dimensions. If you add dimensions, the wedge product is different, but in 3 dimensions, cross product and wedge product, they both have the same formula, right? So they produce a bivector. Okay, so now let's talk about something else. Imagine that you already have the bivector that is A wedge B, that is this directed area, right? And now we have a new vector, a vector called C. And you want to perform this operation, A wedge B wedge C. What do you think will happen? Take a moment, maybe pause the video and think for a moment. If taking the wedge product from 2 vectors gives a directed area, what happens if we do the same operation with 3? It could be kind of obvious probably for some of you. So the result is a trivector. Oh, sorry, I forgot something. I forgot the other videos. Sorry. Because this is a video. Yeah, this is also a video. I forgot to tell you something. So the result of a cross product or wedge product that we said that is a bivector is similar, or computing the bivector from A and B, from A to B, is similar to extrude A through B. Okay, this is also very important in terms of perceiving this geometric interpretation, right? So A cross B or A wedge B creates a bivector, this area, which is basically the same as extruding A through B. Great. Yeah, sorry I missed that. So let's return to the other animation. And here we can see that what we obtain is a trivector, which is a directed volume, and is basically like taking the original bivector and extruding the bivector now through the vector C. And this is what we obtain. And this is an animation of what happens with these 3 vectors that by taking the wedge product or a triple wedge product, you obtain the trivector. In particular, in 3 dimensions, trivectors are not as interesting. Not as interesting, sorry. So we will not use them, but in general, it's good to understand like the entire set of operations, at least in 3 dimensions, that you can obtain using this concept of wedge product in geometric algebra, right? So you pass from a vector that is a directed length, then a bivector, directed area, then a trivector, a directed volume. But trivectors, we were not practically used them too much. Okay, so now let's go back to 3 to the max, and we will do a very simple coding example that helps to understand how vectors and positions behave, and like play with them. And the result of this coding example is it will be something interesting. Okay, so again I have A and B, 2 positions in space, right? And we already know that they represent a position and they have a corresponding vector, right? Okay, so what I want to do is I want to create another object. So let's say it will not be a sphere. So I will go to helpers, point. So is this object that is just representing a point in space. Okay. And let's put a name on this guy. So let's call it Chester. I usually call Chester to this experiment objects. Okay, so what I want is I want to create a code that can animate this object, right? Moving from this point to this point. Okay, so let's first play a little bit with the code. I will go to scripting, Max Script Editor. And something very important, remember, I am using Trees to the Max as supporting software. You don't need to have it installed and you don't need to code what I'm doing here. The reason of that, it's very important that I explain the reason. The reason of that is I will do several examples, like live coding examples of a lot of topics during the lectures, right? And some of those topics will be very related with the assignments, right? Sometimes I will explain like the specific details from the assignment using live coding, and specifically for the bonus points, which is the most important part, the most interesting part, right? The thing is, if I do live coding explanation of those things using exactly the same programming language that is required for you and using exactly the same platform, I am basically doing your homework, right? And so that is not the idea. So that is why I will try to use different platforms to explain certain concepts. So it's your job to watch the material and somehow translate everything. For example, if I am coding in MaxScript, translate everything into JavaScript, right? And obviously it will be a bit challenging, but that's the idea. Okay, so great. So I will define first two variables for these positions, right? So I will define variable A. It will be the position of the object A, and B, it will be the position of the object B. Okay. Okay, so if I want to make Chester to travel from point A to B, I need to compute the vector from A to B, right? And at this point, you probably already know that in order to compute a vector from 2 points, you need to make a subtraction, right? Again, that is the linear algebra knowledge that we assume that you already have. And you need to always remember this thing that is very important. The direction of the resulting vector, right, when you compute a vector from 2 points, depends on the order of your subtraction, right? So it is always goal minus origin, right? So if I want to go from A to B, the origin is A, the goal is B. So it will be B minus A. So I will create vector 1 equals, those are positions, so I can say B minus A. Sorry, B minus A. MaxScript is a language that is not case sensitive. Yeah, but I always try to keep my variables exactly, I mean, if I am using uppercase or lowercase. Yes, so now, yeah, this is just a vector, right? If I run the code, if I open the listener, so the listener is this window here in which you can see the results of your code. With Control D, I can erase it. If I hit Control E to compute it, this is A, this is B, and this is this vector B minus A. Okay. Then I need to animate Chester, right? So the way I can do a very quick animation is I need to activate the animation keyframes, blah blah blah, in Trees to the Max. So I will say animate on. I open and close brackets, and then I will say for t in 0 to 100. These are my keyframes. And then at time t, right? So whatever I put inside, so here I'm like turning the animation on. I am looping through all the keyframes. So this is my animation here, right? So I have from 0 to 100 keyframes, and then just at time t, at whatever frame, I can do whatever I want. So for example, I can say Chester dot pause dot x, sorry, x is equal to t. So if I run the animation, well, of course, I have an error because Chester is not defined yet, right? So if I want to use that name inside, I need to say that Chester is equal to the object Chester. Yes, either in MathScript, you either call the objects directly or the nodes directly by putting this symbol, or you just create a variable, right? So if I compute everything, I will see that now Chester, it has an animation. The thing is, the scale is very tiny. So this position here is, yeah, this is not even inside a unitary vector, right? And t is going from 0 to 100. So I can say, for example, t over 100, right? And I should see, yeah, now I should see Chester moving, right? Okay, so now, okay, how can I now get Chester to move along this vector, right? Well, vector has a direction already, and it has a magnitude, right? And if I multiply that magnitude over by a half, or by a quarter, or by some multiple, right, I can get all the different positions along that, right? By the way, I will take Chester and I will go to Object Properties. That is this window right here. I will set that I want to see the motion path. And why is not working? Sorry, motion path. Yeah, so this is the path from Chester. Okay, so I have that vector already, so I will say vector 1, right? Vector 1 times t over 100. Makes sense, right? Because in the end, t goes from 0 to 100. We want to multiply the vector v1, vector 1, sorry, by some multiple, right? So it needs to be from 0 to 1, right? Because we want to be either at the origin and then moving along that vector until it reach its total length, right? So we just divide t over 100, and let's see what happens, right? And by the way, now I have Chester.pos.x, so I need to change this, right? Because it's not only the x position, but now it will be the entire position, right? So I will just hit, and now Chester is moving in a different direction. But something is wrong. What happened? I am computing the vector from this position to this position, doing this subtraction. There are many books in which you can see vectors in different parts of the Euclidean space, and that they tell you that if you just subtract those positions, you get the vector. And yeah, that is true. The thing is, conceptually speaking, you can draw vectors in any place on your Euclidean space, right? But if you're using data like we are using right now, if you're using only 3 real numbers, right? Those vectors in the end, they start from 0, right? So when you compute this vector, right, the resulting vector is actually here, right? As you can see, it has the same length, right? The same length, and it has the same direction. It's just starting from 0. So we just need to do something else. We just need to add an origin, right? We need to add a position from starting, right? A starting position. And in this case, what is my origin? It will be A, right? So what happens if I have the vector A? Remember, a position, it has a vector, a corresponding vector, right? So the vector A, and I add it to this vector that I computed, I will get the parallelogram, and I will get here, right? Let's see what happens. So I will say plus A, I computed, and great, that's nice. Now Chester is traveling along this line. Good. So now I will create I will maybe hide this window for now. I will create another object. Okay, I will create another object. I will call it C. I will change its color. And now I want to make Chester to travel now from this point to this point. Okay, let's see. So I need another vector and I need another object, right? So in this case, I will create another object. So this will be C is equal to the object C, and I need to say vector 2 is equal to C minus B, right? Because now it's C minus B because I want this direction, right? And for now, I will just copy this line. I will not erase or change this line. I will just copy this line. I will not erase this. I will just create another variable. I will say that this is C4, and I will tell you why it is C4 later. So I will say that this computation here, I will call it C4, and I will say that now Chester is going on the vector 2, right? And now the origin is the position B. So now this is the resulting animation from Chester, right? Now it's traveling from B to C. Good. So now I'm doing another experiment. Now I want to, I still have a variable, now it's C4, that is traveling from A to B, right? And I have now this position that is traveling from B to C. So now I will call that position C5, right? So I will copy this, and this will be C5. And now I want to make Chester to travel from C4 to C5. And you will see that the result is interesting. So this will be C5. If I want to make Chester travel, I need another vector, right? Now I need a vector from C4 to C5. But that vector can't be outside, right? Because this is changing, the position of C4 and C5 is changing through this animation. So I need to do it here. So I will say vec3 is equal to C5 minus C4, right? And I will, yeah, exactly. So now this will be vector 3, and the origin now is C4. So let's see what happens. Oh, I have a problem. Yes, I'm just missing a T here. Yes, so this is the result. So it turns out that now Chester is traveling in a curve. Let's move these guys a little bit and compute it again. And you might recognize this curve. This curve is a parabola. And it turns out that this curve is a Bezier curve. So Bezier curves are super important tools in computer science, in computer graphics in particular, because we use them to interpolate animations. We use it to interpolate, we can use it, for example, for interpolate lines. We use it for animation. We can use it for modeling, and we will use it for several things. We will use it specifically for parametric modeling and creating surfaces automatically using Bezier curves. So yeah, this is a Bezier curve, and this is how you code it. So I'm already show you how you code a Bezier curve. There are other ways to code it that are actually a little bit more efficient. We can use Bernstein polynomials, and I will explain that when we have the actual topic of Bezier curves. But yeah, but for now it was I wanted to make it like a short experiment to show you the difference between vectors and positions, and just this thing that sometimes be confusing, that understanding that vectors are always start from the origin and all that stuff. Great. So I will just give you at the end a couple of tips and tricks. So because we are using real numbers, right? And you have sometimes we have this like rounding problems for floating points numbers. I wanted to just say something. For example, if you want to compare, if you're coding and if you want to compare, for example, two different angles, right? So imagine that you have two pairs of two vectors. Maybe you are measuring, for example, the angle of two different triangles or whatever, or different directions or whatever. But imagine that you have something like that. You want to compare, you have four vectors, right? And you are computing an angle theta and another angle that is whatever, alpha. And you want to compare those angles to see if they are the same, right? So you can compare, for example, the dot product. The thing is, in computer graphics, because everything is just real numbers or floating numbers, things are not usually the same, right? By tiny fractions. So please never use. So if you're, for example, let's imagine that you are computing, two dot products, right? So let's imagine that you have dot product 1 and dot product 2. Right? You have two variables that they already contain the dot products, and those are the dot products of two different angles. And you want to compare if they are the same, right? So instead of saying 1 is equal to dot 2, this can lead to many problems, right? Because it's very likely that they will, although they are geometrically the same, it's very likely that they will not be the same because floating points, right? So usually the way you compare floating numbers in computer graphics, again, it just happens very common in computer graphics, is it's by making a subtraction, for example. So instead you subtract those numbers, right? And you compare if the subtraction of those numbers or the difference between those numbers is less or equal to sigma. And sigma should be just a very tiny number, right? So this is the way you usually can compare numbers. And again, it's very useful in particular for dot products and things like that, right? Because we usually have this problem. And the same happens with, if you want to, for example, check if two vectors are orthogonal or if two vectors are the same, please never check if they are equal, if the dot product is equal to 1, right? Or if the dot product is equal to 0, because most of the time it will not be equal to 0 or it will not be exactly equal to 1, right? So instead of that, you can use this trick, right? Or you can say, for example, if you want to check if two vectors are orthogonal between them, you can check if the dot product is less or equal sigma, right? So yeah, it's similar to this. There's another thing that I wanted to discuss that is related with matrices. So I will just jump into the presentation. Okay, so the last thing that I want to talk about is, that is related with matrices, is if either you use column vectors or row vectors. It is relevant because different technologies uses different notations, and it is different in terms of coding. Okay, so first, in terms of notation, is that different books use different notations. So some books use column vectors, usually the ones that are written by mathematicians, and other books they use row vectors, right? So row vectors, they look better in a book because, right? I mean, they can like align with a paragraph. But column vectors, they look better in equations because in the end, a vector like combined or multiplied by a matrix can represent a linear system, and it is way more convenient to represent a linear system with the matrix on the left side, the vector on the right side, and yeah, it's just more convenient, right? But the thing is, in terms of programming, depending on which paradigm you're using, is the way you multiply the vectors times these matrices, right? So again, the vector is just a set of real numbers, and from the mathematical perspective, they are also a matrix, right? So if it's a column vector, and I want to multiply times a matrix, I need to pre-multiply the matrix, right? So the matrix needs to be on the left side because it's matrix times the vector. If I use row vectors, it's the opposite. I need to multiply the vector times the matrix. So the matrix is on the right side. And in particular, talking about the technologies, right? You will see that there are two main technologies in computer graphics, DirectX or OpenGL. So DirectX uses row vectors, okay? And OpenGL uses column vectors. The assignments that you will do are based on WebGL, and WebGL is based on OpenGL. So the code that you will need to do, it uses column vectors. So in previous editions of this course, this has been a problem all the time, but people always forget that it is, because it's OpenGL, is using column vectors, and the way you construct your matrices and the way you construct, you multiply your matrices on your vectors, it's different, right? And if you don't remember that, you might have problems, a lot of problems, right? And yeah, that can be bad. So, for example, if you are reading a book, right, and you are reading a book and you're, for example, trying to construct a rotation matrix, and that book is written in row vectors, that matrix that you just read in the book and copy and try to use it on your code, first, you cannot multiply the matrix on the right side, right? You need to pre-multiply the matrix times the vector. But also, because you're using OpenGL and you will use column vectors, it means that if you copy a matrix from a book that is row vector notation, you will need to transpose the matrix, right? So if you don't transpose the matrix, you will have problems. So yeah, so I think that's it for today. In terms of matrices, I didn't discuss too much. I mean, this was the thing that it was important for me regarding matrices to talk about. Again, because I am assuming that everybody needs to have some linear algebra background. If you think you have a little bit more review in terms of either vectors or matrices, please tell me. Just post a comment on Piazza. The idea was just to give you this geometrical interpretation, and also I would recommend to read these chapters, right? So chapters 4 and 5 from 3D Math Premiere for Graphics and Game Development by Fletcher Dunn. Remember, you have the link on the webpage, and these chapters 4 and 5 are related to vectors. It's a very good chapter, and if you really don't remember anything about vectors, I think you can go there and it will be very interesting. And also for matrices, you can read chapter 7. If you read this, right, and after reading this, you still have problems, again, you just post there and you can say, oh, I really don't understand what is the geometrical intuition of a determinant or something like that, and I can recommend other stuff. There are also some incredible resources on the internet. There's a series of videos from 3 Blue 1 Brown, and that is related with linear algebra. It's incredible. And there's also Zach Starr, also a professor. I don't remember if he's a teacher or a professor. I don't remember, but well, Zach Starr, he's doing amazing math videos, and he has some videos regarding matrices that are just amazing. So you can, yeah, I mean, there's a ton of things in YouTube. I probably eventually try to get some of those, I mean, nice video recommendations, and I will maybe post it on the webpage. So yeah, that's it for today. Thank you so much, and I will see you in the next lecture.